everyone, I'm Nabeel Rehemtulla,
And I'm Theophille du Laz.
and we'll be telling you about our work automating science for the Bright Transient Survey in the Zuki Transient Facility.
The Zwicky Transient Facility, ZTF, detects hundreds of thousands of potential astronomical objects every night. To achieve such a feat, ZTF relies on its very large field of view, effectively tiling the whole sky in only a few thousands of fields. Every new image is compared or subtracted to older reference images, revealing any changes in our night sky. These are overwhelming numbers, but thankfully ZTF is also home to the Bright Transient Survey, BTS. BTS is by far the largest spectroscopic supernova survey ever conducted. In a nutshell, BTS looks at a subset of these ZTF detections that are bright enough, and after filtering out bogus detections and other objects that are not of interest to the survey, it leaves us with a handful of potential supernova candidates. Members of the survey will decide which of those warrant follow-up observations with the SED machine, a spectroscopic instrument found on the P60 telescope, ZTF's neighbor on the Palmar Mountain. Thanks to the spectra obtained by ACDM, astronomers can look for the chemical footprint of any supernova type, confirming an object's supernova-ness and reporting it to the community.
So over the years, BTS has used these two telescopes to discover and classify thousands of supernovae all over the sky. So this animation by Christopher Fremling shows over time where the supernovae we find are and what are their types. Now you'll notice that there are two gaps on this map. The first place we don't look for supernovae is through the plane of the Milky Way, where there's too much extinction of the light. And the second is the southern sky, because ZTF cannot look that far south. Now, after more than 5 years of operations, BTS has assembled a sample of nearly 10,000 spectroscopically classified supernovae. This is the most of any single group in the world. With this sample, we can start looking at the diversity and the populations of these different types of supernovae. So we'll plot this as the brightness of the supernova versus the duration it lasts for. The majority of supernovae we see in BTS are these type 1a supernovae. Now these are important for calibrating distances and studying dark energy. Secondly, we have the diverse population of core collapse supernovae. These come from massive stars collapsing under their own gravity. Now we also see the rare class of superluminous supernovae, which are exceptionally bright, and classical novae, which are very faint, so we can only see them when they're quite nearby.
Since last year, we've now fully automated the BTS workflow. As discussed earlier, this starts with ZTF autonomously detecting an overwhelming number of potential astronomical transients. Each of those detections are sent as alerts to the community and to ZTF's in-house data processing platforms, which already allowed members of BTS to filter out most of the candidates that are not of interest to the survey, using the alerts content. Alerts that contain two very important machine learning scores. The first one is BRI, telling us whether or not the detection is a real astrophysical transient. And the second is SG score, telling us whether or not a transient is a star from the Milky Way, our galaxy, or hosted by another distant galaxy. On top of that, we compute additional features using past detections at a given position, telling us what the candidate's light curve looks like. When did it peak? How bright was it when it did? When was it at its dimmest, and by how much? Using all of these features, including those that are machine learning generated, along with the images from ZTF of known supernovae from the existing BTS dataset, we've trained BTSbot, a machine learning classifier telling us how relevant an astronomical transient is to the Bright Transient Survey. The model runs in real time on every new alert, allowing us to filter out objects with low BTSbot scores. On top of that, we've developed the machinery needed to not only send the candidates to the BTS members for them to identify these transients, but also send instructions to autonomously trigger follow-up observations with the SED machine if an alert passes one of two criteria that decides if an autonomous follow-up is warranted based on the BTSbot scores only, and how to prioritize this target. This effectively mimics the usual human-based workflow to select and trigger on valid astronomical transients. Down the line, a CDM is already equipped since 2021 with SN1A score, a machine learning classifier telling us whether or not a given spectra corresponds to a type 1a supernova. If its score is high enough, it will report it to the community as such. This closes the circuit, and in October 2023 gave us the world's first fully automated discovery, identification, and classification of a supernova, in a much shorter amount of time than what any humans could have achieved, thanks to BTSbot's inherent ability to run in real time with low latency and high confidence. Since then, we've repeated this feat dozens of times and have saved many human hours in the process, leaving more time to BTS astronomers to look for rarer objects.
Now that we have finished developing and deploying BTSbot for BTS, we are now looking at repurposing BTSbot and these integration tools to automatically identify and request follow-up observations for very nearby supernovae. Thank you very much.